All right, so today's discussion is going to be fairly brief in comparison to last chapter. But we're going to start off right off the bat talking about trends of the periodic table. Now, the periodic table itself, that piece of paper that you have in your hand, is far more useful than just what's printed on the surface. Okay, there's a lot of hidden information in each one of these rows and columns. Okay, and a lot of it is based off of this word right here, properties. And so that's what we're going to investigate, because once you get a better understanding of the periodic table, a lot of questions that are asked of you in terms of chemistry, especially and more specifically about elements, you can simply utilize the periodic table to get a very good understanding without even really doing any investigation. And that comes from the individuals who worked on creating the first periodic table over history. And then there's really one that's credited with the implementation and creation of it more than anybody else. So let's get started. And let's talk about a brief history of the table itself. Dimitri, Mendeleev, and then the lesser known individual, Lothar Meyer, independently came to the same conclusions about how elements should be grouped. Okay? And the reason why I say Lothar Meyer is lesser known is because he doesn't necessarily get the credit for developing the table that we have today. Mendeleev is the one that pretty much receives all the credit. There's really a significant difference between the two individuals, not a difference in their ideas on elements and how they should be grouped, but how they went about promoting their table. See, Mendeleev, we're going to watch a brief history of Mendeleev here today as well. Mendeleev was tenacious. He was obsessive. He worked day and night when he started getting these ideas of the table itself and how they should be arranged. And he tried to get it published, as you'll see, but no one could figure out how to really publish his table. And really at the time, they didn't quite know if they could believe it or not in terms of if his table was correct. So instead, he decided to shell out his own money, publish his own book, and put his table out there. And the rest is, as they say, history. So when he was developing his table, okay, at the time, there were roughly 60 or a little bit more than 60 known elements. Today, there are 118 confirmed elements on our table. So he only had close to half of what we have today to work with. And as he was putting this table together, he would make predictions. And he would put these spaces all throughout his table that he said elements should, a particular element should belong here. But we just haven't discovered it yet. A great example is one where he essentially predicted the discovery of germanium. Okay, germanium, if you look at the periodic table, is right there, below silicon. In which, before they discovered germanium, he actually called it ecosilicon, which basically means below silicon when it's translated. And so the reason why he did this is because of how he had his table set up. He has table set up based off of similar properties, periodic base statements of the elements. Okay, and so what he did in his predictions, he said that, okay, this germanium or this ecosilicon, this element that is not known at this moment, is going to go here, and here's what I believe based off of my table the properties of this unidentified element should be. Okay, His prediction for this unknown element with the atomic weight of 72, the density of 5.5, the specific heat, the melting point, the color even, the potential formula, okay? And it goes on from there. Come to find out, he was almost spot on. His prediction of atomic weight of 72, the actual atomic weight of germanium was 72.59. The density where he says 5.5, actual 5.35. Because the table was set up in such a way, he was able to make very accurate predictions of what these unknown elements should be in terms of their properties, even down to their color. Where he says a dark gray, well, in fact, it's a grayish white, okay? Still gray in color, okay? So, his development is what allowed us to make predictions, okay? And that's what we can do with this table still. Even though we've got these 118 known elements, we could still, maybe not necessarily make predictions, but make statements about properties of a particular atom simply based off where they're located in the periodic table. So we're going to watch a little video about the history of Mendeleev, because it's always good to know where we came from and the work ethic that individuals have or had well before what we have today. So let's watch.
Hello, I'm Hank Green. Welcome to Crash Course Chemistry. Today, we're talking about the most important table ever. Not the table where they signed the Declaration of Independence, nor any table of contents, nor this table right here, nor the stone table of Aslan. Nay, it is the periodic table of elements, a concise, information-dense catalog of all of the different sorts of atoms in the universe. Today, I want to talk a bit about the creation of this table, which is, to be clear, one of the crowning achievements of human thought. To start out, though, let's close our eyes and pretend. Imagine you're in Siberia, and you're a 13-year-old boy, and your father, who was a professor but had gone blind, leaving your family of more than 10 brothers and sisters destitute, has just died. I know, downer. Your mom, to support the family, has reopened an abandoned glass-making factory in the small town where you live, largely because she wants to make enough money to send you to school someday. A year passes, the factory burns down. But your mom, she sees your potential. She knows that you have a keen scientific mind and will not see that squandered. So, with your siblings out of the house and on their own, she packs up your belongings, straps them to a horse, and with you in tow, rides 1,200 miles through the Ural Mountains on horseback to a university in Moscow. There, on your behalf, she pleads earnestly and effectively, and they reject you. So together, you ride another 400 miles to St. Petersburg, to the school where your father graduated as a scientist, and as luck or extreme, insane, undeniably Russian persistence would have it, they accept you and your saddle-worn butt as a pupil. Your mother, having completed her mission, promptly dies. If you're doing your imagining as I've told you, you might feel a tremendous debt to your mother and a very deep desire to ensure that you achieve something on par with the sacrifices she made for you. And maybe that's one reason why Dimitri Ivanovich Mendeleev became the crown jewel of Russian science and a theorist who revolutionized how we see the world. Mendeleev spent a great deal of time in laboratories as a student, studying the burgeoning new field of chemistry. He worked with all the elements that you could work with at the time, and his knowledge gave him unique insights into their properties. Those insights would come in handy. Let's all imagine we're Mendeleev again. I like doing that. And that we know a bunch of stuff about chemistry, which, you know, you don't yet, but we're imagining. So it's the 1860s, and about 60 elements are known to mankind, and their atomic weights are mostly known as well. So the simplest thing was just to sort them in order of their atomic weights. But interestingly, you, because you're clever pants, realized that the most significant relationships seem to have nothing to do with the atomic weight. Lithium, sodium, potassium, and rubidium were all extremely prone to reacting with chlorine, fluorine, iodine, and bromine. Beryllium, magnesium, calcium, and strontium were all similar but less reactive. But with a quick inspection, you, and to be fair, a number of other chemists, realized that there was a relationship between atomic weights, but it's periodic. At the beginning of the list of elements, characteristics repeat every 7 elements. On a side here, we now know that it's every 8 elements, but in the 1860s, elements were studied based on their reactivity, so the non-reactive noble gases had not yet been discovered, so the period occurred every 7 elements. As the mass of the elements increases, the repetition starts to look a little less periodic, though it's certainly still there, it just isn't perfect. Some of your colleagues, they're saying, well, such is life. It was perfect repetition early on, but later in the list it gets a little fuzzier. But not you. You become obsessed. Obsessed with the perfection of the periodicity. You write out the names and weights and properties of elements on cards, you lay them across your desk, shuffle them, tear them to pieces in frustration until one day you realize that you're simply missing cards. The numbers aren't working, not because there's something wrong with your ideas, but because some elements simply haven't been discovered yet. Armed with this insight, you insert gaps into the table, and things suddenly fall perfectly into place. 7 element periods for the first 2 rows with hydrogen in its own category, 18 element periods for the next 2 rows. You're so certain that you predict the properties of these missing elements. And when a French scientist comes along and says that he has in fact discovered one of them, you argue with him, saying that you discovered it first in your mind. And when you see his data and it doesn't match yours, you publish a paper saying his data for the new element he discovered is wrong. That's how certain you are of yourself and this beautiful new theoretical framework you've created. And you know what the really crazy thing is? You're right. That French guy's data was wrong. You, never having examined the element he discovered, knew more about it than he did, because you are Mendeleev, master of the elements. Okay, we're done imagining for the episode. That was fun, though. The different groups Mendeleev had identified are a lot of the same groups that we study today. Starting at the left, we have the soft, shiny, extremely reactive alkaline metals, so reactive, in fact, that they have to be stored in inert gases or oil to prevent them from reacting with the atmosphere. Alkaline metals want nothing more than to dump off an electron and form a positive ion or cation, and they're always jonesing to hook up with a hottie from the other side of the table. So, of course, seeing as they're so reactive, you don't find hunks of them lying around in nature. Instead, chemists must extract them from compounds containing them. Next, you have the alkaline earth metals, reactive metals, but not as reactive as the alkaline metals, forming cations with 2 positive charges instead of just 1. Calcium, shown here, undergoes a very similar reaction to sodium and water, just a little more slowly, producing a little less heat. The middle body area of the table is made up of a nice solid rectangle of transition metals. These are the metals you think of as metals, with iron and nickel and gold and platinum. The majority of elements are metals. They're fairly unreactive, great conductors of heat, but more importantly for us, good conductors of electricity. They're malleable and can be bent and formed and hammered into sheets, and they're extremely important in chemistry, but overall surprisingly similar to each other. On the far right, just over from the noble gases, the halogens make up a set of extremely reactive gases that form negative ions or anions with 1 negative charge and love to react with the alkali and alkaline earth metals. The rectangle between the halogens and the transition metals contain a peculiar scattershot of metals, metalloids, gases, and nonmetals. These guys don't end up as ions unless you take extreme action and start shooting other ions at them, so generally a bit boring over here, though lots of interesting covalent organic chemistry. We'll get to that. Down below, in their own little island, are the Lanthanides and Actinides, metals that were largely undiscovered in Mendeleev's day because they're so similar that it's next to impossible to separate them from each other. And finally, on the far, far right, also undiscovered when Mendeleev built his chart, the completely unreactive noble gases. Like a lot of other obsessive scientists, Mendeleev never thought he was done with his table. So he held it back for quite a while, only publishing it as part of a new chemistry textbook he was working on as a way to make some quick cash that he needed. And as with many other scientific revelations, there were a number of other people hot on this discovery's trail. As many as 6 people published on the periodicity of elements at roughly the same time as Mendeleev, but a few things set him apart. 1, he was obsessive. He knew the data better than anyone else, and had spent a ton of time working on a theory that many people thought was just an interesting little quirk. And 2, he realized in a way no one else did that the idea of periodicity had far-reaching consequences. It seems as if he had a deep belief in the cosmic importance of what he was doing, almost a religious fascination. Mendeleev believed in God, but also he believed that organized religions were false paths to the unknowable nature of God. I like to believe that he thought he saw some divine pattern in his tables, and Mendeleev felt as if he was coming to know God in a way that no other man ever had. To be clear, this is pure conjecture. And as we now know, the periodicity of elements is a physical phenomenon. It's a function of electrons, which are in some ways pretty dang peculiar, but certainly not at all mystical. But we'll get to that peculiar physical reality in the next episode. The periodic table that we know and love, I love it anyway, is a representation of reality, a way of understanding and sorting the universe as it exists. But that form of the table is not by any means set in stone. Indeed, a contemporary of Mendeleev envisioned the table set onto a screw or cylinder with the elements wrapping around from one side to another. While Mendeleev's table looks more like a map up on a wall, de Champ-Courtois, a geologist, envisioned more of a globe. Unfortunately for de Champ-Courtois, no publisher could figure out how to print his cylindrical three-dimensional table, and so he published his paper without a graphical representation of his periodic cylinder of the elements, and it was largely ignored. I guess they didn't have papercraft back then. I am a huge fan of this cut and tape model of the periodic table. You can make your own, there's a link in the description. And there are also a ton of other designs for periodic tables that have various advantages over the one that we're all familiar with. Our periodic table as it stands is really a little bit unhappy with itself, frankly. The Lanthanides and Actinides really should be part of the table, but we separate them out because it's hard to fit that on a piece of paper. Really, this is what it should look like. And really, it would be best if it wrapped around into a circle so that fluorine and neon and sodium were all next to each other, instead of being on the opposite sides of the map, because they're just one proton away. Mendeleev's contribution, nonetheless, is more powerful than at first it seemed. He ended up forming a guide to help future chemists understand things that wouldn't be discovered for 25, 50, even 100 years. Indeed, after Mendeleev's theories were published and accepted, the overwhelming cry from the scientific community was, why? Why? And though Mendeleev was not himself concerned with this stuff, he actually denied the existence of atoms, or indeed anything he couldn't see with his own eyes. It turned out that the answer to the first why was the electron. That sneaky little electron, Mendeleev, if he'd been around to see their discovery, he would have hated them. But you will have a healthy respect for them after you learn all about them on the next episode of Crash Course Chemistry. Thank you for watching this episode of Crash Course Chemistry. If you were...
All right, so nice little history about the periodic table, and also a statement that was made towards the end there, where our table, as it stands now, isn't necessarily the best form of it, but it's right now it's the most. I don't know if it's useful or, the word is escaping me now. I'll think about it later. But anyway, in this chapter, as we progress through chapter 7, we are going to rationalize the observed trends in the sizes of atoms and ions, ionization energy, and electron affinity. But there's also some other trends that we are going to be looking at as well. And that first one is called effective nuclear charge. So when we have what's called a many electron atom, so basically anything other than hydrogen that has more than, anything that has more than one electron, the electrons are going to be kind of torn in a couple ways. They're going to be both attracted to the nucleus, because what's inside the nucleus of every atom? Protons. Protons have what charge? Positive. Electrons have what charge? Negative. Opposites attract. So the protons in the nucleus are always trying to keep a hold and pull on the electrons in the same atom. At the same time, also in other atoms. But that's neither here nor there at this point. But when you have an atom that has multiple electrons, they also, when they're out and about, outside the nucleus, they don't want to be near each other because they have the same charges. So they try to repel. So these poor electrons are getting pulled in towards the nucleus, repelled by other electrons outside the nucleus. And so what's the nuclear charge that we describe for each atom, the electron experiences depends on both that attraction and repulsion. Now I have down here, just a friendly reminder or a refresher. What is a valence electron? We talked about it late last chapter. Yes, they are the electrons in the outermost energy level. So we're going to look at a term today called core electrons. Okay. Remember, raise your hand if you remember doing the noble gas configuration for electron configuration. Remember doing that, where you put the noble gas element? You got to shake your head so I can see. Okay, like this. When we did those noble gas electron configurations, those noble gases stood in for everything before it. Remember that? How it was a representative, it was a stand-in for all the electrons that came up before that noble gas. Those are what we call core electrons. Okay? The electrons not in the outermost energy level. And those terms, valence and core electrons, are going to be big when we discuss effective nuclear charge. And so, first thing we look at is what we actually call, or what we're going to see in our readings if and when we open our book, is that effective nuclear charge, we call it Zeph. The letter Z is typically assigned to protons from way back in the day. Okay? And so if we want to calculate effective nuclear charge, or Zeph, we simply take Z minus S. Well, again, still doesn't make any sense. Well, Z is the atomic number, which we're given on every element. And S is what's called the screening constant. The screening constant is typically the number of those core electrons that I just mentioned. And we're going to talk more about these core electrons. We're going to talk briefly, or not briefly, but we're going to talk more about the effective nuclear charge here on this next slide. Don't write anything yet. Let's talk about these trends. And then I'm going to show you how we translate that to our periodic table. So, first trend is effective nuclear charge, or Zeph. It increases from left to right across any period of that periodic table. So as we go from left side all the way to the right side, we're going to have an increase. I'm going to explain to you why after I read to you why. The reason why Zeph increases left to right is because the number of core electrons remains the same across a period. But as you go left to right, the number of protons increases. Okay? So imagine a tug of war. One side is, actually, what you say on this, Mr. Jeffers? Say it. Okay, I get to be the mighty nucleus. Okay, so I've got protons. You are going to be the core electrons. Okay, you are going to not be attracted to me, but you're also going to be repelled by other electrons. But what you also provide is a shielding element to those valence electrons. So you're kind of helping protect. You're kind of like a fence to the valence electrons. I'm trying to get you, or get those valence electrons to pull them closer. You're trying to say, no, you can't do that, right? So we're doing like a tug of war type of thing. We're pretty evenly matched, 1 and 1. Okay? I'm an old man, take it easy on me. But now what happens if I have Bolton come up here? Come on up here. Okay? I'm going left across the table. Come on up here. Okay? I've just added another proton. He's going to remain the same. His number of core electrons is going to remain the same. How do you think this tug of war battle is going to start going? What do you think is going to happen? Are we going to have a fair fight, or is he going to start being pulled this way? There we go. He's going to pull this way. Dan, come up here. I've moved another. I went left a little further to the next element. You're on our side still. We're still in the same period. So you're going to be, yeah, it's dripping. It's raining inside here. So come on over. You don't have to necessarily, there you go. So she's now a new proton again. But my same number of core electrons remains the same. Now, you see what's happening. as we go from left to right, we're increasing the same number of, or we're increasing the same, I can't say it, we're increasing the number of electrons while the core number of, there's a lot going on in my head. We're increasing the number of protons, there we go, while keeping the same number of core electrons. So we are having a much greater effect on pulling those electrons closer to the nucleus. That's enough. And so, thank you. So that's what effective nuclear charge is really the overall pull that the nucleus, more specifically the protons, are going to have on those outer electrons. And so that trend here is going to impact another trend that we're going to talk about tomorrow. Okay? So again, that's going left to right, and I'll come back to that here. And so again, as we go left to right, those core electrons cannot protect. They cannot shield those valence electrons very effectively because they're starting to get outnumbered. And so we're going to start seeing atoms shrink and become smaller as we go across the table. Talk about that tomorrow. Going down from top to bottom of a column, the effective nuclear charge experienced by valence electrons changes far less because as we go down a down a column, those valence electrons begin moving further and further away from the nucleus. So when you move further and further away, it's like magnets. Okay, when you move magnets further and further away, they have a much less attractive pull on each other. So as electrons move further away, those protons really loosen their grip simply because of distance. And so on your periodic table, this is how you're going to write your first trend. And you can do it on any part of the table, top or bottom or side, okay? But this is just kind of how I do it. And you want to make sure we're going to have approximately 6 to 7-ish or so trends. So you want to make sure that you're going to have enough room, okay? So plan accordingly. But here's my periodic table. Wonderful, isn't it? All right, so what I do here is we were first told in our notes that going from left to right, okay, Zeph, if you want to write effective nuclear charge, you can, but Zeph increases. No, I've done a really nice thing because I'm that kind of guy. At the very end of your notes, you have a couple of slides that go over and provide you what direction each of these trends we're going to talk about go. Okay, so if you ever forget one, you have a reference in the very back. Okay, now, as your note stated, that effective nuclear charge is much less dramatic going down. But a lot of places, if you search it, will still go ahead and say that Zeph going down will increase too, because it does increase going down, but just slightly. Okay? So, oops. This is what you should have on your periodic table now. Again, some people put it down here on the bottom where they go left to right, Zeph increases. It doesn't matter. Okay, as long as you have the trend on there. So, again, what I want to show and highlight is let's look at what element do we want to do? Let's look at nitrogen, okay? If we did nitrogen's electron configuration, we're going to have 1s2, 2s2, 2p3, right? So if we were to do this in the noble gas configuration, okay, it's going to be what? What noble gas or what where am I going to start now? Helium. Okay. And then I just continue on there. 2s2, 2p3. All right. Now remember, helium represents the core electrons. Okay. Now let's look at oxygen. Okay. Let's do oxygens. 1s2, 2s2, 2p4. Doing oxygen's noble gas configuration, what noble gas am I going to use? Helium again. 2s2, 2p4. Again, still represents that. I went one element to the right of nitrogen. Yeah, my valence electrons increased by 1, but what also increased by 1? Starts with the P. Protons. What didn't change? The core electrons. So these two little core electrons, little security guards, remain the same. At the same time, we are adding protons as we go across the period. So their ability to protect these valence electrons decreases because we are increasing the number of protons. We're increasing the number of particles that can pull those valence electrons in. And these two little soldiers right here, they just can't protect and screen that attraction very well as we keep going across that periodic table. Okay? So that's what I'm talking about with effective nuclear charge, okay? The security guards, their numbers stay the same as we, kind of have the increase in valence electrons and protons that are trying to attract each other. Okay. So that is all for today. So again, make sure you bring those periodic tables every day. And if you want to,